So we are just on time. I think if you agree, we can start now.
Yes, this is fine with me. Can we make sure that everybody can hear me?
Okay. If anyone have any problem with the sound, they can raise their hand. Just on the bottom of the part where all the students are writing, all the people who are participating to this session, you have a tool allowing to raise your hand. It means that you want to say something or mention that you have some trouble. Well, if you find anything wrong or are not able to hear, normally it's okay. Then raise your hand and we'll try to see what we can do. Generally, it depends on your own audio problem. So I'm very pleased today to introduce Professor Triantafillou, Thanasis Triantafillou from University of Patras, well-known professor in the field of FRP strengthening and having done a lot of work in the field of seismic retrofitting. And I'm very pleased to introduce Professor Triantafillou in this session. So for everybody, welcome, good morning or good evening, depending on where you are in the world. We have very different people from different places, so welcome everybody. Thanks to participate to this 8th webinar of the year of the IIFC. And then Thanasis, I think you can start when you want.
Okay, thank you very much, Manuel. Also from my side, let me welcome everybody to this short lecture on seismic retrofitting of concrete and masonry structures using composite materials. Good morning or good afternoon or good evening, whatever, that really depends on where you come from. It's a real pleasure to have you around, and without spending any more time, I would like to move directly to the structure of my presentation. I will start with a brief introduction on the topic, and then I shall present concepts and some also details on seismic retrofitting of reinforced concrete structures with regards to flexure, shear, as well as confinement. We will also present some case studies on the topic, some examples. Then I would like to spend some time on seismic retrofitting of masonry. Masonry structures, unreinforced masonry structures, subjected to in-plane or out-of-plane actions like flexure or shear, also for confinement. Again, we shall see some case studies. And if time permits, I really hope so, we will we will present some relatively new concepts on the use of non-polymeric materials for seismic retrofitting of concrete and masonry, and the presentation, of course, will close with a short summary and the basic conclusions. I don't really know your background, the background of the class of the students in this area, so I will spend a few seconds, a couple of minutes, to present the basics. We are talking about fiber reinforced polymers, FRPs. These are composite materials made of fibers in combination with a typically polymeric matrix. These materials are available in mainly two forms. They are available as rigid elements, as you see here to the left. So we have strips or laminates, and also they are available in the form of flexible fabrics, as you can see to the right. So we may have carbon fabrics. You can see the typical black color of carbon here, glass, aramide, as well as other types of fibers. And those fabrics are typically unidirectional. They have fibers, carbon, glass, aramide, etc. in one particular direction only. So these are the two basic elements we are talking about. If there is only one thing that we should know and we should remember about those fibers that we use to make composites, polymer-based composites, FRPs, this is the one here. This is the stress versus strain plot for typical fibers. For example, the red line is the one for carbon. Glass is here at the bottom. Aramide is somewhere in between. And all those stress-strain plots are compared with a simplified one for steel, just to illustrate that those fibers go linear elastic all the way to failure. There is no yielding, there is no plastification, there is no plateau, as is the case with steel. So those fibers go linear elastic all the way to failure. They do fail, they do fracture in a brittle way at very large stresses and at relatively high strains as well. Well, those strains depend very much on the type of fibers. For carbon, they are in the order of 1.5%. For glass, in the order of 2 up to 3%. Aramide is somewhere in between. So let's remember that those fibers go linear elastic all the way to failure. There is no yielding, there is no plastification, but still those materials are, as we shall see later on, are quite good and quite effective in retrofitting in the seismic retrofitting of other materials such as concrete or masonry. In this slide, I have tried to summarize the advantages above this yellow line and the disadvantages of FRPs, of fiber-reinforced polymers, with regard to retrofitting, to seismic retrofitting. Those materials are light. They have a low weight, which is in the order of 1/4, 1 divided by 4, in comparison with steel. They are resistant to corrosion. They are available at extremely long lengths. So we can have strips or fabrics, tapes, several decades, several hundred meters long. Because they are lightweight, they are very easy and very fast to apply without major disruption of occupancy. As we saw before, they have extremely high strength, 4 or 5 times higher in comparison with steel. They do not modify the geometry, the properties, the geometrical properties of cross sections. We will discuss that later on when we shall see some examples. Last but not least, we can construct jackets. We can make jackets. That is, we can wrap structural members with these materials without modifying the stiffness characteristics. The stiffness does not change. It practically remains the same. In fact, that one may be thought as a disadvantage if we have a structure, if we have a building that is quite flexible and we want to increase the stiffness. Those materials are not the ones to be used to do that. It's not possible to do that by jacketing. Again, all these concepts will be discussed later on. On the negative side, they are expensive, much more expensive than steel. They are not ductile in the sense that they do not have a yielding plateau. However, they are highly deformable, so we can actually get a lot of ductility from structural members retrofitted with composites. as they are made of polymers, they are made by the combination of fibers and polymers. They need to be protected against fire. And of course, we as engineers need to learn more. It's not one of those materials that we typically learn a lot about during our undergraduate or graduate studies, or there is some kind of lack of education. And I hope that this course can help a little bit in this direction. I'm sure that we will get back to those points a little bit later on. Before starting with the so-called FRP strengthening technique, I have tried to summarize in this slide here other methods, other techniques that we typically use in seismic retrofitting. For example, we can use reinforced concrete. We can use shotcrete. We can make jackets outside existing structural elements, reinforced concrete jackets to increase the strength, the stiffness, as well as the ductility of members. We can use steel plates. This is the so-called steel plating technique. We can do metallic jackets, steel cages. We can use steel cages on the outside of columns, for example. Steel plates can also be used in columns, or perhaps we can increase the dimensions of existing structural elements by adding reinforcement as well as concrete. So this is just a summary of some of the basic techniques. We have a few more, but this is where we are in most typical situations. Now let's talk a little bit about our technique. The idea here is to use FRPs, to use those composite materials in a different ways. What we see here is the so-called basic technique. What is the basic technique? We have two variations. One is to use rigid elements, strips, like the one shown here, or like the one shown here to the right. Those strips are bonded externally, typically on the tension zones of structural members, beams or slabs, for example. They are bonded through the use of epoxy resins to increase, for instance, the flexural resistance. Those are relatively stiff elements and typically straight elements. They are prefabricated. And all we need to do on site is to use a high quality epoxy resin to bond them externally. What is most common, by far most common in seismic retrofitting, is to wrap structural elements using fibers. And this is a typical example here. You can see a column which is wrapped with carbon fibers. This is another example. This guy here is wrapping this column that is adding fibers in the circumferential direction to increase the shear capacity or the ductility, as we shall discuss later on. So to summarize, we have two basic methods. One is related to the application of rigid elements, which are typically used in flexural strengthening. The other one relies on wrapping of structural members using flexible fabrics. I would like to say a few things about flexural strengthening. Flexural strengthening of beams or slabs is not so common in seismic retrofitting. Anyhow, this is the basic concept here. This is the typical response of a flexure-dominated member, such as a beam or a slab. If you plot load versus deflection for such an element, what you get is this red curve before doing any intervention, before strengthening. However, as you add external reinforcement on the tension side of the member, you get some increase in strength. Of course, at the same time, you get a reduction in ductility, in deformation capacity, and there is very limited, if any, increase in stiffness. And as you increase the amount of external reinforcement, that is, as you increase the thickness of those externally applied strips, then you move from this green curve to the bottom up to the one to the top. That is, you have a higher increase in strength and maybe a little bit of higher stiffness, but more reduction in ductility. Speaking of ductility, it should not be surprising that we get this reduction in ductility. This is not due to the fact that we add FRPs. Even if we added steel, we would have this reduction in any case because we increase the amount of tension reinforcement, so that should not be surprising. As I said before, flexural strengthening in seismic retrofitting is not very common. Flexural strengthening, of beams or slabs. What is more common is sometimes is flexural strengthening of columns, especially if we have to satisfy capacity design requirements. That is, if we need to increase the flexural resistance of columns in case they are weak in comparison with beams. How do we do it? Definitely not as shown to the left. This is not the way to do it. This is not the way to do it. I repeat. This is a classical example that some people do. What you see here is the addition of carbon-based laminates on the tension faces of columns. This is definitely not going to work in when you have seismic loads, because clearly your bending moments are maximized in this region near the ends of columns, which means that we need to extend the tension reinforcement all the way through the joints. We have to anchor this reinforcement through the joints as illustrated here to the right. So external bonding of FRPs from bottom to top of a column will not work. In seismic retrofitting of columns, we have to extend and anchor this reinforcement all the way through the critical regions through the joints. Not only this, at the same time, we need to confine this reinforcement externally by doing some transverse wrapping with fibers. Those fibers are placed in the horizontal direction. That is, we make a local jacket at the ends of the members, basically to prevent local buckling of the externally applied reinforcement in the tension zone. One example of doing this, of adding this external reinforcement, is the so-called NSM, that is near surface mounted reinforcement. What is near surface mounted reinforcement? We make some grooves. We make some grooves inside concrete near the surface, at the surface. We fill them with an epoxy resin, as you see here, and then we add longitudinal rebars made of FRPs. We could use steel, stainless steel, for example. So we insert those rebars, those FRP rebars inside those grooves, and then we fill the rest with epoxy, and that's it. It's like adding extra tension reinforcement in the tension zones. A couple of comments regarding detailing. This is a sketch of what I was describing before. You see the longitudinal FRP rebars placed inside grooves here, and you can also see the transverse wrapping with horizontally placed fibers to control, to prevent, to delay buckling of the this longitudinal FRP. This is one option. A second option is to use a tape, a fabric, a unidirectional fabric along the height, along the length of the column, starting from bottom all the way to the top. And since it is practically impossible to anchor this fabric beyond the critical section here, we can use the so-called spike anchors. Those are bundles of fibers. Half of each bundle is inserted inside a groove here. The other half is spread on top of our unidirectional tape, the fabric, to ensure continuity and to ensure transfer of stresses from the tape, from this fabric, from this external fabric, into the anchorage region. So we have at least those two concepts. At the bottom here, you can take a look at typical axial load versus bending moment interaction diagrams for columns before retrofitting, before strengthening in flexure. That's what you see at the bottom by this solid line. And after strengthening, that is after adding external reinforcement in the tension areas, which is represented by the dashed line, the outer line. It's quite interesting to observe, to conclude that if axial forces are high, our external reinforcement is not that beneficial. It is quite effective, quite beneficial. That is, it increases the flexural capacity from here to there. So we have an increase in the flexural resistance of our columns only if axial loads are low, which is typically the case in seismic retrofitting. We typically design our structures for low axial loads. So you can see the increase in flexural resistance as a function of the applied axial load. Here is a comparison of what we get in terms of load versus drift, that is versus horizontal displacement divided by the height, by the length of the column. This comparison is done for two cases. In the left, you see the typical response of a column without any retrofitting, without this extra flexural reinforcement. To the right, you see an identical column which has been strengthened. So you can see that there is a clear increase in the capacity. The flexural strength before was, that is the horizontal load, was 33 kilonewtons. It increases up to 48. So there is a substantial increase in flexural capacity. But then when our external reinforcement fails at this point, we have a reduction, which could be gradual depending on how exactly those externally applied fibers would fracture. I would like to talk a little bit about shear strengthening, which is probably one of the two most important applications of FRPs in seismic retrofitting of reinforced concrete. The second one being confinement, which we will discuss a little bit later on. What is the objective in shear strengthening? The objective is to increase the shear capacity. You can see a typical plot of, let's say, applied shear, horizontal load in a typical column versus horizontal displacement. What we want to do here is to increase the shear resistance of the member so that brittle failure modes, like the one shown to the left, are transformed to ductile ones. The whole idea is to add fibers pretty much perpendicular to the member axis, that is to wrap columns or even beams with fabrics so that fibers are perpendicular to the axis of the member. And this is, we can think of this concept as equivalent to having externally placed stirrups, let's say an infinite number of stirrups on the outside, on the perimeter of those members. So you can compare the typical response of a member before shear strengthening to that after strengthening. Of course, when it comes to design, the question is how to calculate the properties, that is the thickness of the jacket, that is the number of layers needed, so that the shear capacity will be increased by a fixed amount, and that we will discuss in a moment. In this series of figures, of sketches here, you see typical configurations of FRPs used in shear strengthening. For example, in the case of beams, of T-beams, we have a number of options. This is what we should avoid. This is the so-called two-sided jacketing. In this case, we simply bond FRPs on the two faces, on the two sides of the webs. The other option is to use the FRPs all around the webs. This is a so-called three-sided jacket. This is far better than this one here, because we have better anchorage, better bond conditions of the jacket. This is even better to anchor the jacket, to anchor the three-sided jacket inside the slab using spike anchors. I will get back to this in a couple of minutes. Alternatively, we can use, instead of using continuous fabrics, we can use strips at a certain distance, at a certain spacing, to make closed jackets, to make loops all around the web, which would behave in a way very similar to the internal stirrups. In this case, we anchor the vertical legs of those jackets inside the slabs, which is quite beneficial. It can be done by using a continuous system, by doing wrapping, or it can also be done by anchoring the ends of the jacket, of the strips, in the slab that is in the compression zone, by placing those elements inside grooves in the compression zone. When it comes to columns, things are typically much easier. We normally have access all around columns. In this case, we can fully wrap the fabrics all around so that we have closed systems. In this case, the fibers are fully wrapped all around the member. In case of columns or in case of shear walls, and that's by far the most effective strengthening system, to have this full wrapping all around the cross sections. Some photographs of how it is done. It is straightforward. You have the member here. You really have to apply the tape, the fabric, all around the column to make those jackets. The gray or the white spots, the white areas here in the right are this is silica sand, which is typically applied is typically thrown on the last layer of resin in order to make a rough surface, so that one would be able to apply plastering or rendering that would hide the jacket and at the same time protect it against fire. A few more photos. In this particular example, we have in situ impregnation of the fabric with resin, with epoxy resin. wrapping of the column with this fabric. We go all around, or wrapping of this beam. In this case, we make a three-sided jacket all around near the ends of the beam where shear forces are high to increase the shear resistance. Other examples, both good and bad. This is another typical example. One can use strips at a certain spacing or continuous fabrics. This is another possibility. This is the profile with yellow or white, whatever it is. You can see the profile of an inverted T reinforced concrete beam, which is wrapped with fabrics at a certain spacing. This is definitely not the way to do it. This is wrong because if you think that tension is applied to the jacket, if the jacket is activated to carry shear forces, it will have to carry tension, and this tension will result in local debonding here in those reentrant corners due to a resultant force that goes outwards. In that case, one should have to apply perhaps some kind of local anchorage. So let's try to be careful when it comes to the practical execution. Okay, let's talk a little bit about calculations. I promise not to show you too many equations. I will try to show you just the basic ones. The design of jackets, that is the calculation of the thickness of the jacket. Or in other words, if we know the thickness of a single layer, we're talking about the calculation of the number of layers needed to get to a certain level of shear resistance. This is done in a way very similar, identical, I would say, to the way we calculate the amount of internal stirrups. The only thing we have to do is to add to the contribution of the internal stirrups, it is this term here, the contribution of the externally applied reinforcement, the contribution of the FRP. That's the basic difference, and all we have to do is to estimate, to calculate this second term. This second term can be calculated by using a formula that is identical to the one that we use for internal stirrups, except that we don't use a yield stress here. We don't have a yield value for the stress in the FRP. Our material is linear elastic to failure, as we discussed before. It is a non-yielding material, so we have to use a value of the stress in the FRP, the so-called effective stress, when the material fails at shear failure of the member, and that has to be estimated. That really depends on the failure mode. So that would be our formula if we use strips at a certain spacing, and that formula generates to that one at the bottom if we use a continuous jackets. That is an infinite number of strips at practically zero spacing. I said before that this effective stress in the fibers used in shear strengthening depends very much on the failure mode. And you can see here what happens if those jackets are not closed, if those fibers do not follow the profile of the cross-section, do not go around the cross-section. When the shear crack forms, it's not very clear in this photo, I'm sorry. You can imagine that there is a diagonal crack here. When that crack forms, then those fibers, those strips debond. The same is the case with the fabric. If you have a shear crack, if you have a diagonal crack here, the fabric will debond due to the tension, due to the fact that the fibers are subjected to tension and they are not anchored. That can be prevented if those fibers would be continuous all around the cross-section. So this is the reason why I emphasized earlier, let me go back to this slide. Yeah, here it is. This is why I emphasize that having full wrapping, having the fibers all around the members is much more effective in carrying stresses in shear strengthening. Okay, let's go back. What can we do if wrapping all around the cross section is not practically feasible? We can use anchors. We can use, for example, the so-called spike anchors. These are bundles of fiber. This is just a bundle of fibers. Half of it, in half of it, the fibers are straight. They go inside the slab. In the other half, the fibers are spread on the jacket. I hope that you can see what I'm talking about here to the left. So you place those anchors at a certain spacing along the length of the beam, and by doing so you are able to transfer stresses from the jacket to the compression zone, that is through the slab. Those anchors are actually quite effective, and to prove this, let's take a look at some graphs which show the percent increase in shear resistance as a result of strengthening for different cases. For example, what is this? This is, in this case, we have a 39%. In this case, the shear resistance increases by nearly 40%, 39%, in comparison with the control specimen. By adding, for example, 2 layers of carbon fibers, we can increase the capacity by nearly 40%. By using a U-shaped jacket, a 3-sided jacket. If we anchor the same jacket using those spike anchors placed horizontally in the web, that increases 50%. So this is better. But it gets much better if anchorage is according to the way that I described before. That is, if we use those spike anchors with half of their length inside the slab, so that stresses are directly transferred from the jacket to the concrete. Of course, if we increase if we decrease the spacing of the anchors, that would be even better. But the main concept is that we need to combine those U-shaped jackets with spike anchors at a reasonable spacing. This is much more effective in comparison with the 3-sided jacket without the anchorage. Let me just say one word about beam column joints, which typically fail in shear. We quite frequently get diagonal failures, shear failures after earthquakes in these elements if we don't have a continuity of stirrups inside the columns. The way to apply the fibers in this case, for example, would be what is shown here. We need fibers optimally in 2 directions. We need the horizontal fabric as well as one with fibers in the vertical direction. So that inside the joint panel, those fibers are in both directions and they are quite effective in carrying shear. To make sure that they would work inside the joint panel, the fibers, those fabrics should be anchored outside the joint area. For example, by using those transverse FRP tapes or maybe metallic ankles or any kind of anchorage system you can imagine. The idea is to make sure that the fabrics are anchored beyond the joint area. Typical results of the response of joints. This is a control specimen without any retrofitting, so you see the shear force in the joint versus a measure of displacement. The response of the same joint, of an identical one, if we use a single layer of a given material, one layer of a low thickness carbon fabric, and that's where we go if we use a couple of layers. So there is a substantial increase in strength, 40% for one layer, 65% for 2 layers, etc. And also there is increase in the dissipated energy. And a couple of photos on how those fibers are applied. We have both horizontally placed as well as vertically placed fibers in the joint area. Okay, perfect. Confinement. Confinement is the, again, probably as I said before, probably the most interesting application of FRPs in seismic retrofitting. We do confinement for mainly 4 reasons. The one that is not so much related to seismic retrofitting is illustrated here by confining concrete with FRP jackets. You increase the strength of concrete so that you can increase the axial capacity, the axial resistance of the member. If we need to upgrade columns, piers in a bridge, for example, due to heavier traffic load, that would be the way to do it. However, in seismic retrofitting, what is much more interesting is to do local jacketing, that is to wrap the ends of columns with local FRP jackets in order to increase the deformation capacity. By this local confinement, we increase the failure strain of concrete in the compression zones here, down here, and by increasing the ultimate strain of concrete, we can develop higher deformation. So the member is much more ductile. This is the whole idea. We also do this local jacketing in case of lap splices. If we have lap splices at the bottom of columns, for example, to prevent failures, that is to prevent debonding, slippage of the rebars in those lap spliced areas, we can take advantage of the confinement provided by the fibers. Last but not least, we can take advantage of those local confining jackets to prevent, or better, to delay local buckling of the internal rebars, of the longitudinal reinforcement. I will spend a few minutes on each of those applications in my next slides. Before doing so, let me just illustrate how easy it is to do those jackets for confinement. Labor is quite limited. The material is extremely lightweight, so it can be wrapped easily around members without major disruption. So in most cases, we have a clean job. And okay, let me skip this. Yeah, that's an interesting series of photos. You see this local confinement I was talking about earlier at the base of columns. These are cantilever type elements. Confined, well, not cantilever, I'm sorry, we have the local jackets on the top as well. Those are columns confined locally with FRP jackets at the bottom as well as on the top to increase ductility. This is not done for axial capacity. This is done locally at the ends of the members to increase ductility. I will not really spend a lot of time on the basics of confinement. I hope that most of us are familiar with the topic. The whole idea is to wrap concrete all around with the fibers in the circumferential direction so that when concrete expands due to the application of axial compression, those fibers on the outside are activated in tension, just like internal stirrups do. And by doing so, those fibers return compressive stresses in the concrete, and those lateral compressive stresses, this lateral compression results in increasing both the strength and the ultimate strain and the deformation capacity of concrete. And that increase depends on the thickness of the jacket, that is on the volume of fibers, that is on the number of layers that we use in the circumferential direction. You see here, for example, with those very many red curves, how the stress versus strain response of FRP confined concrete changes with the thickness of the jacket. As the number of layers in the jacket increases, you have a higher strength as well as a much higher deformation capacity. So, question, when does this system fail? By the ultimate strain of concrete. That depends on the deformation capacity of the fibers. The system, such a member confined by FRP, will fail when the fibers in the circumferential direction will fracture, when they will fail in tension, when the tensile stresses, the hoop stresses, become equal to the tensile capacity of the jacket. So the higher the deformation capacity of the fibers, the better for the response of the member. This is why high deformability fibers such as glass are better than brittle fibers such as carbon in this particular application. To do calculations, we need to somehow quantify the response of confined concrete. That is, we need the confinement model. If you search the literature, you will find at least a couple of hundreds of those models. Nearly all of them, if not all of them, can be expressed in this way. This is a general form. For example, the equation to the left gives you the strength of confined concrete normalized with respect to that of unconfined concrete as a function of the confining stress. Here this term sigma LU, whatever design value of that, is the confining stress. And we have an identical formula for the ultimate strain of confined concrete normalized with respect to the ultimate strain of non-confined concrete. So clearly, the higher the confining stress, the higher the strength as well as the ultimate strain. If I go back, this confining stress depends, as we can see here, by simple equilibrium on the thickness of the jacket, on the strength of the jacket, as well as on the dimensions of our cross-section. Once this model is available, well, that's a very simple model for circular columns. One could generalize that model, could extend it to the case of rectangular cross-sections. A simple way to do this would be what I have sketched here. You can estimate the confining stress by taking the average of two confining stresses in two directions, and by estimating this average in its direction, by the way, is presented here. Of course, there is the so-called confinement effectiveness factor, alpha F, in this equation, and that effectiveness coefficient, this confinement effectiveness factor, depends on the shape of the cross section. It would be equal to 1 for rectangular cross section. For circular cross sections, but then it would be much less than 1 as the cross section becomes rectangular with a high aspect ratio. This confinement effectiveness coefficient basically is basically defined by the ratio of the confined area, this is the effectively confined concrete area, divided by the total area of the cross-section. And clearly that depends on the shape of the cross-section, on the aspect ratio in case of rectangular cross-sections, on the radius at the corners. This is why we really have to maximize this radius to increase the area of this shaded shape here. In case of using strips at a certain spacing, which is not very common, we have to reduce this coefficient even further to take into account the fact that confinement is even less effective in between those strips. And also, if those strips are applied at an angle with respect to the horizontal, then this effectiveness coefficient reduces even further. But again, this is not a common case. So what maximizes confinement in rectangular columns is we should try to keep the ratio of the two sides as close to 1 as possible, and we should try to maximize the radius at the corners. I talked about increase of deformation capacity. This is what I refer to. This is the response of a typical column before retrofitting with FRPs. We reach a ductility factor that is relatively low, let's say 2, 3 maybe, and by locally confining the column, that is by locally applying the fibers at the ends of the column, we increase the capacity of the member, we increase the ultimate strain of concrete so that the member can deform more. In that case, ductility goes up, but this is not the case for strength, and that we should try to remember this. This is a very important point. This local jacketing is only an effective means of increasing ductility. We only increase the deformation capacity, which can be quantified by the chord rotation. Chord rotation is defined here in this figure, the so-called theta. This is the angle between the axis of the member and the chord of the member at its deformed configuration. So that theta increases. Also the respective ductility factor, mi theta increases, as well as the curvature ductility factor. This is the main reason that we do this local jacketing in seismic retrofitting, to increase the chord rotation or the respective ductility factors. That is illustrated by comparing the response of two identical columns, one without any retrofitting, an identical one with retrofitting. This is wrapped with a couple of layers of carbon fibers at the bottom. You can see the column. It is a cantilever type member subjected to cyclic horizontal displacements. You can see, I will try to zoom if possible here. You can see how the member fails. I hope you can see the zoom. You can see the typical failure of the column at the base in the compression zone. We have spoiling of concrete, local backing of the longitudinal reinforcement, which is not the case if the member is wrapped with this local jacket with carbon fibers at the base. Those carbon fibers would fail due to tensile rupture. So by comparing the response of the two, we conclude that again, there is practically no difference in the strength. However, there is a tremendous increase in deformation capacity. Ductility goes really high. I am not sure that everybody is able to read numbers. I can assure you that the drift values are quite high. We are talking about horizontal displacements in the order of 100, if not more, millimeters, corresponding to a column height in the order of 1.6 meters. So that's a very high drift. Let's see how we would do calculations. Again, we don't have the time to discuss the details, but at least we can take a look at the basics. The whole idea is to express the chord rotation of the member at failure. This is the ultimate chord rotation. This is expressed as a function of the curvature at failure. This is the ultimate curvature of the member. The ultimate curvature is defined by the ultimate, is calculated by dividing the ultimate strain. This is the maximum strain, the compressive strain in the concrete, divided by the neutral axis. By wrapping the member, we increase this value here, the value for the ultimate strain, and that can be calculated from our confinement model, the one discussed before. So by increasing that, we get a higher value for the curvature at failure, which in turn results in an increase in the chord rotation. So the chord rotation at failure increases, as well as the respective ductility factor. An alternative approach would be to calculate this ultimate chord rotation would be to use empirical formulas like the ones which may be found in Eurocode 8. This is copied from Appendix 3 of Eurocode 8. Those formulas give, in an empirical way, the ultimate chord rotation as a function of different parameters like the reinforcement properties, the volumetric, the mechanical ratio of reinforcement, the shear span, the height of the cross-section, but most important, as a function of the confinement of the volumetric fraction of fibers in the cross-section. It is this term here. So for a given value, for a target value of the ultimate chord rotation, one can calculate the number of layers, the thickness of the jacket that would result in such a value. That's the third application of confinement, preventing failures at lap splices, as we discussed before. If we have short lap splices, the response of our member would be something similar to what is shown here. By confining this lap splice region with fibers, one can change this, modify this brittle response to a nice ductile one, as illustrated to the right. The whole idea here, of course, is to increase the friction between spliced rebars. I will not really go into the details of the derivation of these formulas, but by applying external compressive stress, confining stresses, we increase the friction, and by using a friction model, we can calculate the thickness, the required thickness of the jacket, that is the number of layers, so that this frictional failure, this failure at lap splices would not develop. Last but not least, one can rely on semi-empirical formulas like the ones shown here to calculate the required thickness of the externally applied local jacket to delay buckling of the longitudinal reinforcement. Well, let's try to wrap it up, to summarize. We have to assume that our intervention does not result in stiffening. We have to make sure that stiffening of our member is not a requirement. If that's the case, then we should design jackets for the target shear resistance. That is, we should do shear strengthening of the member if needed, of course, so that we satisfy capacity design requirements. Then we need to design jackets for the target deformation capacity, that is for the chord rotation or the ductility factor. And then the jacket thickness corresponding to the previous step, to step B, should be checked and modified if needed, if rebar buckling controls or if we expect lap splice failures. I hope that this example can make this story a bit more clear. Let's assume that using the models that we discussed already, we have calculated that we need, for example, 4 layers to increase the deformation capacity, the ductility. We need 2 layers to prevent lap splice failures, 3 to control, to delay rebar buckling, and 2 layers to prevent shear failures. In this case, we apply 2 layers all along the height, all along the length of the column, and we add 2 more at the ends, so that we have a total of 4, and by doing so, we satisfy all requirements at the same time, the shear resistance as well as all the other failure modes. We should remember, though, that again, we don't increase the stiffness, we do nothing about second order P delta effects, and we don't increase the flexural capacity of the member. This is only for ductility as well as for shear resistance. There is no improvement with regard to the flexural resistance of the member. A case study is what follows here. This is an example of a building that was retrofitted a few years ago in the south part of Greece, in one of the islands. It's a 4-story building which was retrofitted through the use of approximately 800 square meters of carbon fibers. The job was done in a very short period of time. That was the prime requirement in this intervention, to have the job done as quickly as practically possible, with the building nearly in full operation. The objective of the retrofitting was to increase the shear resistance in many structural elements, as well as the ductility. What you see here is the base shear in the two principal directions of the building as a function of the top displacement. In black, you see the response, the capacity curve of the building before retrofitting in two directions, and in red, the capacity of the same structure after retrofitting, which shall be described in a second, the way it was done. Again, take a look at that there is only an increase in the deformation capacity. There is practically no modification of the stiffness. The green indicates the demand in terms of top displacement. And that was achieved by shear strengthening of the columns where needed, by shear strengthening of the beams, basically at the ends where shear forces are high. By shear strengthening of the beam column joints, flexural strengthening in some of the cantilevers was also done in this particular project. And you can also see some typical construction architectural drawings illustrating the detailing of those interventions. Shear strengthening, local jacketing for ductility, shear strengthening of beams. You see the 3-sided jackets, full wrapping of columns for confinement, etc. And a typical plan view illustrating all the different interventions. Again, red is for confinement, blue is shear strengthening of beams, red is also for shear strengthening of columns, yellow is flexural strengthening of cantilevers, purple is strengthening around in the perimeter of areas where some holes had to be created, etc. I think we have to speed up a little bit, so I will skip my second example to talk about, to spend some time on seismic retrofitting of masonry with FRPs. I hope that this simple sketch, this simple figure, illustrates how an unreinforced masonry structure typically fails after earthquakes, during earthquakes. And the failure mode depends very much on the type of element we are talking about. For example, we may have shear wall type elements subjected to in-plane shear. Those would fail by diagonal cracking. We may have walls, masonry walls, subjected to out-of-plane bending. In these cases, we expect flexural cracking, vertical in this case. We may have column type members, such as the one shown here, subjected to in-plane flexure. Those would behave like columns, like unreinforced concrete columns, subjected to bending in combination with axial loading. Or we may have beam type, again, short beam type elements subjected to a combination of flexure and shear. So depending on the action, depending on the type of the structural element, one has to think, to conceptualize and design the retrofitting scheme. How do we typically do this retrofitting today? By adding reinforced concrete, by shotcreting unreinforced masonry on both sides. That is by constructing reinforced concrete jackets. Well, they don't necessarily have to be as thick as illustrated in this figure, but this is the concept to make a sandwich by adding lightly or heavily reinforced concrete on the two faces. This is a so-called reinforced concrete jacketing technique, which is illustrated here. We need steel reinforcement and also shotcreting to provide for the outer faces of this sandwich. The method is quite effective in terms of strength, ductility, stiffness, etc. However, it suffers from a number of problems which I have tried to list here. We increase the mass of the structure, we increase the stiffness, we increase the thickness, the dimensions, as a result of which we modify the dynamic characteristics of the buildings. The buildings become stiffer and heavier, thereby attracting higher seismic forces, which of course is a disadvantage. The method is labor intensive. It is we have obstruction of occupancy, and of course it is not always applicable, especially in cases like the one shown at the bottom. If you have very nice buildings, old buildings with arches on the facades, one cannot make those shotcrete jackets to cover those arches. So what can be done? What is the way of doing things? Let's take a look at some typical examples. Let's assume that we are talking about out-of-plane bending of walls. We need fibers to play the role of tensile reinforcement in the tension zone. If we talk about in-plane flexure of let's say vertical column, vertical masonry elements, again we need fibers placed in the vertical direction, either concentrated in the tension zones or evenly distributed. If we're talking about in-plane shear of masonry, in-plane shear, then we should apply diagonal strips or perhaps fabrics or even fabrics on the full area, on the full surface of the wall. We can even apply strips at a certain spacing. We can insert FRP rebars inside bed joints and then hide them with mortar, so that we provide tension reinforcement that would increase the shear capacity, the in-plane shear capacity. When it comes to confinement, we need horizontal. We need the fibers placed horizontally to confine, for example, rectangular in-plan structures, domes, or even columns. A few photographs to illustrate the concepts. These are some photos illustrating the application of diagonally placed carbon strips to increase the in-plane shear capacity. The same concept here. That's a photo from Iran taken a few years back to do the same job. That's from a school building in Greece. Again, the idea is to have those diagonally placed elements to play the role of tension reinforcement. Out-of-plane bending of vaults, of arches, can be controlled. The behavior can be improved by eliminating a certain number of plastic hinges which would develop at failure of such members. For example, you may have an arch. This arch, subjected to earthquakes, would fail through the formation of hinges, or the number of hinges, those hinges, the formation of those hinges can be prevented by adding external reinforcement on both sides, if possible, on one side, if it is not practically feasible. Some photos, most of them from a few of my good colleagues in Italy. You see consolidation of domes by using carbon fibers on top or sometimes underneath, at the bottom. Same story here. Yeah, that's an interesting application. That's one of the earliest applications of FRPs in dome-type structures, illustrating the possibility of using transparent fabrics. This is a glass fabric using a special type of resin, which does not really affect very much the aesthetics. The fabric itself is transparent, so the intervention, the jacket is not visible. That's another example related to confinement. You see the use of CFRP tapes replacing corroded steel tendons at the base of this dome. A similar application, we have full wrapping of rectangular in-plan buildings using carbon tapes at 1, 2, 3 levels here. 1, 2 levels in this photo to the right. Similar example. Photos from full wrapping of columns. That's a typical masonry column. The bricks are exposed prior to wrapping the fibers. A photo of the same columns after wrapping with glass fibers, and then the finished columns where plastering has been applied and some decoration and painting, etc. Again, the same concept, confinement through full wrapping of columns from top to bottom. Okay, well, there are many applications worldwide. Let me just say only a few words about calculations. Unfortunately, time is not enough to give all the details, but the least we should remember is that we should apply concepts very similar to those used in the dimensioning of reinforced concrete. For example, we can idealize masonry as concrete without any internal steel. And just to give you an example, if you have a wall subjected to out of plane bending combined with axial load, this is, let's say, a typical cross section. We need external reinforcement in the tension zone, in the tension area, to carry tensile stresses and increase the flexure capacity. We need to take a look at strain compatibility, to look at equilibrium of internal stresses in the cross section, and by considering this equilibrium, we can calculate the depth of the neutral axis, and also we can get the required surface required area of this external reinforcement to reach a target value of the resisting moment. Likewise, for the case of in-plane flexure combined, for example, with axial loading. There is really not much to say here, except for the fact that we just have to use already known concepts for reinforced concrete. The only difference here is that our reinforcement is a non-yielding material, is a material that goes linear elastic all the way to failure. Another example, in-plane shear can be calculated by idealizing those horizontally placed fibers in a way analogous to stirrups in reinforced concrete. Confinement, again, all we need is a confinement model, very similar to what we have discussed already for concrete. And by using this model, we can calculate the thickness of the jacket, the number of layers, so that one could reach a target value for the strength or for the ultimate strain of the masonry. We don't have that much time left, but still I would like to spend at least 5, maybe 10 minutes maximum to discuss an alternative technique. One that is actually quite similar to what we have been talking about so far, to the FRP strengthening techniques, the only difference being the type of materials used. There is a number of problems associated with polymer-based composites. Some examples are the following. We discussed this already. We have a problem with the poor behavior of the resins, the epoxy resins, at high temperatures. Also, those resins are quite expensive. Sometimes we are not allowed to use them. If we're talking about strengthening of monument-type structures, old masonry buildings structures, resins are not compatible. We are not allowed to use them. If we do seismic retrofitting and if we make jackets, by using FRPs, it may very well be the case that damage behind those jackets is not visible. For those and also many other reasons, we have been trying for the past 10-15 years or so to replace polymers, to replace epoxy resins with mortars, with cementitious materials, with inorganic materials, so that the matrix in the composite is a mortar-based one, and the fibers, of course, are not unidirectional fabrics, but they have to be in the form of a textile with an open architecture, as illustrated in these photos, so that we have a good mechanical interlock between the fibers and the matrix and the inorganic material and the mortar. That's the whole idea. This is a material which one can call, one can use the TRM the term TRM to characterize it. TRM standing for textile reinforced mortars. These are the well-known FRCM materials in the US literature. Fabric reinforced cementitious matrix composites, etc. Again, the concept is to replace epoxies with an inorganic matrix and to use fiber materials in the form of a textile with an open architecture so that we have good bond characteristics. That can be used to do local jacketing, to increase the ductility of concrete. As illustrated here, that would be the response of a reinforced concrete column without this local jacketing. You see a typical failure at the bottom. And you see how this column would behave if it is confined by a locally applied FRP jacket. And you get an identical response if this FRP jacket is replaced by a textile-based one. So one can conclude that the effectiveness of those TRM jackets is pretty much identical to that of FRP jackets. The concept has been validated doing small scale as well as full scale, nearly full scale experiments. It has been proved that those TRM jackets perform extremely well. They are for confinement as well as for shear. Their application is by far more interesting in masonry, in unreinforced masonry, in comparison with concrete, mainly due to the fact of the compatibility issues. Those materials are friendlier, they are more compatible to masonry substrates, and also because of the fact that stresses are typically multidirectional on masonry walls. Those bidirectional textiles are quite more effective than the FRP fabrics. One can prove that by doing simple tests. I will only show you some typical results. For example, if you have a shear wall, a masonry wall subjected to in-plane shear, the response of this member in the absence of jacketing, in the absence of strengthening, would be what is illustrated in red by the red curve. If you retrofit it using a single layer of an FRP, that is of an epoxy-based jacket, you would get what is illustrated in black here. If you do a TRM, a textile-based jacket, you get what is illustrated in black to the right. By comparing the two, you see that TRM is nearly as effective as FRP, and by far more, and we get a much higher increase in capacity in comparison with a control specimen. Same story for masonry subjected to in-plane bending in combination with axial load. TRMs are quite effective. You have substantial increase in strength as well as in ductility, which is even higher in comparison with FRPs. I would like to just illustrate, just go to nearly the last of my slides. This technique is quite interesting to also strengthen infill walls in reinforced concrete frames. In an attempt to make infills work together with the surrounding reinforced concrete structural elements so that structures become stronger and stiffer. This has been tested in nearly full scale relatively recently. You see, for example, a 3-story, nearly full scale reinforced concrete frame with masonry infills. The frame was tested without any strengthening, and the response is, in this case, is what illustrated by the red curve. And also after strengthening with those textiles, after covering the area of the walls and the surrounding frames with those textile-based materials, and that is illustrated by the solid, by the black curve. You can clearly tell the difference. The damage is limited, is reduced. The strength is increased by nearly 50% in that particular example. The deformation capacity also gets higher, etc., etc. So it is really an interesting concept for the case of infills in reinforced concrete frames. I believe that this is the last of my slides. I think we have had enough for today. Let me try to wrap it up. Let me try to give you the main conclusions. I think the FRP strengthening technique is easy, fast, and quite effective. Easy to apply. It is quite fast and quite effective when it comes to mechanical behavior. In order to do calculations, we need to have in mind some basic principles. Number one, forces in FRPs are carried only by the fibers. The material is linear elastic all the way to failure, and it has a large deformation capacity. It can be used to increase the flexural resistance of beams, slabs, and columns, to increase the shear capacity, the shear resistance of beams, columns, shear walls, and joints, to do confinement in columns, not only for the axial resistance, for axial capacity, but mainly for ductility, to increase the deformation capacity. And last but not least, the so-called TRM, that is the textile reinforced mortar technique, can be thought as a supplement, I would say, as an alternative and as a supplement actually to the FRP strengthening technique. It is an interesting concept which will probably pave the way for even more applications of those beautiful materials in the field of seismic retrofitting. With that, I would like to thank you very much for your patience and for your attention. We can use the facility to the right the window to maybe make comments or to provide some, to ask some questions if there are any. Again, thank you very much.
Thank you very much, Thanasis. Very, very interesting presentation. So is there any comment or question you would like to ask? You can use your microphone if you have one, or maybe, okay. Does the model on confinement effects on lab splice have been already published? Are you aware about some publication about this topic?
Certainly, there are at least a couple of publications. Should I type my response, or can you hear me?
Everybody is hearing you, so maybe the person make.
Yes, there are already publications on that.
Okay.
Not only on that, but also on the model on confinement effect of on delay in rebar buckling. Do we need spike anchors with TRMs? Well, that's a very good question. We have tried that. In fact, we have developed a special type of spike anchors using textiles. If we do U-wrapping, if we do shear strengthening in beams, TRMs are much more effective if we anchor them with spike anchors, if possible, using locally epoxy resins or with any kind of anchorage. We always need spike anchors or anchorage if we have open jackets. Well, we don't need them, but we increase the effectiveness of the strengthening system when we deal with open jacketing. So the answer is yes, we need some kind of anchorage when we use TRMs in open jackets.
Okay, thanks very much. And I was wondering about how to get the value of strength of those spike anchor is quite complicated. There is a lot of testing procedure, and there is no one that can be used. There is some pull-out test, but these tests don't consider reverse loading. What's your opinion about how to qualify those kind of products?
Well, testing of individual spikes is one thing. These tests have been done. As you say, clearly they're not very easy, but one can do them. But I think one should test the complete system. One should do tests on members strengthened with jackets, with or without spike anchors, to quantify the effectiveness of those anchors. Because by testing the system, you get a better understanding. Testing a single anchor does not necessarily give you how the anchor will work when applied on a jacket and when used in combination with others. So it's still a hot topic for research, and there is plenty of room to do research in this area.
Okay, so maybe one last question.
I think there is already a question written. Don't we need always to do pushover analysis to consider FRP effect in design? Yeah, if we do assessment and retrofitting, pushover analysis is always an option. What is the advantage of FRPs? In our analysis is that the stiffness characteristics, as we discussed already, the stiffness properties of our structures are not modified. So, only the strength, the shear strength increases, and the deformation capacity. So we can analyze our structure twice, before retrofitting and after retrofitting, by doing pushover, for example, without having to modify the stiffness properties. Okay, so yes, pushover is the way to do the dimensioning, the design.
Okay. Any other comments or questions? You can introduce yourself also and have discussion if you prefer. If not, I would like just to thank you again. Very nice presentation. For everybody, this presentation will be available in replay the replay, you can access it from the IIFC website. It's very easy. And then it allows maybe you, or if you have colleagues that are interested by this talk, to see it again later. Well, if there's no question coming, I would like to thank you again Thanasis, for this very nice talk. I think we have a large overview about the FRP capacity for seismic application, and well, see you soon in a conference or elsewhere.
Certainly. Also, I would like to thank you very much for the kind invitation, and to thank all the students for their participation. Thanks and goodbye.
Thanks. Bye-bye.